Hi there. My name is Brennan Marsh-Armstrong. I'm a medical student at UCSD who just spent a year doing research at the UCSD Simulation Center. And I'm going to talk to you about how a process of very simple, what I would describe as sort of garage science, allowed me to go and solve a problem the UCSD Simulation Center has, which is also a problem which biohackers at large might have. So, in so doing, helping you guys with the stuff you got going on. So, medical simulators. They're an important tool for medical students to learn procedural skills that they need to learn to be capable in the hospital. They're an important tool for physicians to be able to rehearse and practice the skills in a safe environment. And they're important for biohackers to be able to practice and refine tasks that they in turn might need to use for augmentation and modification. Um, Simulators come in a wide variety of functionalities and sort of different levels of complexity. You have something as simple as a silicone pad, which can be used to suture up stitches to practice suturing and closing wounds. You can have something like a lumbar puncture model, which can be used to practice putting a needle into the spine for a variety of different reasons. You can have paracentesis models with ultrasound capability, and you can work your way all the way up to more complex models on the right, like multi-part endotracheal intubation procedures for putting tubes into the throat to breathe for people, and models that have complex ultrasound capabilities that allow you to practice ultrasound and seeing different internal structures. The thing about these models is they're highly variable in cost. So on the left there, you see what's called a blue block, or abbreviated as a blue block, which is one of the most commonly used procedural trainers in medical school. It's just a simple silicone pad or simple silicone block rather with some vessels inside of it and is ultrasoundable and as a result costs about $600. I guess you can imagine for all of you who are familiar with the sort of rough cost of silicone, that's a pretty big markup on the raw material cost. But it can get even more extreme than that. If you add a simple injection molded plastic surrounding to it and essentially make the exact same thing, you can make a central venous catheterization model in the center there that runs for about $3,000. And this, if you start adding things like ultrasound capability that lines up with the models themselves, or the ability to do things like measure and simulate vitals by things like balloons that inflate in the chest, you can start adding zeros onto the price tag. You can imagine this can be highly problematic for this simulation centers that are training novices that would potentially need to get a little rougher with these sort of things and make more mistakes than otherwise would be commonplace. And for biohackers that are having to teach these skills to themselves or are doing more creative, more interesting things with models like this, or presumably with the human body down the line, but might need a step along the way to practice putting in implants, doing procedures. You can imagine the prices rack up very quickly. So the first step of the process that I did for innovating and changing this at the UCSD Simulation Center was looking at the blue box and realizing I can make that. It's just a block of silicone, and it's not even a complex shape. So, broke open a CAD software. I'm partial to Fusion 360 because I'm not a genius that uses SolidWorks and just created roughly a cylinder, cut it in half, put some vessels in it, and made it out of silicone. It's a process of 3D printing what you make in CAD, making a hard silicone exterior, and then pouring ballistics gel to get your final product. Now, something that is interesting is that ballistic gel itself doesn't have echogenicity, a term here meaning that when you look at it under ultrasound, it has color or sort of density to it so that you can see the vessels. But it does have echogenicity? Flour. And flour is cheap. So you just put a little flour in there, who knows how much, just a little sprinkle, and mix it in, pour it into your silicone mold, and you have a ballistic gel model. Even including the cost of all the things needing to make it, including the silicone, the ballistics gel, that cost about $50 down from 600. And on top of that, it is not only cheaper to make, but it is reusable because ballistics gel can be remelted down either with a heat gun to close off needle marks that have been made in it, or just simply tossed into the oven and remade. So that $50 goes a lot longer than one model that will eventually give away because you can just keep reusing and reusing and reusing and reusing ad infinitum. Um, on the left here, you can see the raw materials that were used to make it. Nothing that you couldn't purchase at a local craft store yourself, with maybe the exception of that liquid. But I'll give you a secret here is that even though that's supposed to be this really fancy blood mimic material or blood mimic liquid that we use, as you can see, that's pretty pink, and that's because I just bought food coloring and added it to water. Okay. So in terms of ultrasound ability, on the left here, you'll see the blue, that's a picture of the blue block. That's sort of what we are mimicking in terms of trying to give medical students the ability to see inside the body. You see the black, which is a vessel. You see the needle, which is designed to be echogenisic. And you see the path when you put the ultrasound probe in line with the needle of it going into a vessel. It's an important skill to learn. And if you were to do things like, I don't know, design and work on your own insulin pumps or work on anything that might need to be taking out or putting things into the bloodstream, this is a view you'd want to get to make sure you did the job. By comparison, here's the model that I made and what it looks like when you access it. So as you can see, the needle's advancing and it looks pretty gosh darn similar. Should say I'm not an expert, so I nearly hit the back wall there, but when I can take out fluid and I can inject fluid back in, that's that. Looks pretty similar. So from there, the Simulation Center already started using those and has been since. But I wanted to get a little more complicated because all that does is let you inject into a vessel. And that is pretty useful and certainly saves a lot of money, but you can get more creative. And it actually happened by accident. So what I was doing was I was trying to pour one of these basic blocks and I made a mistake and it had a dent in it. And so I tried to pour, literally just hand pour more ballistics gel on top of the mold. And it kind of worked, but it was really easy for me to peel off. But then I realized, hey, you can put two pieces of ballistic gel right next to each other, and it on ultrasound looks like a fascial plane. Now, what a fascial plane is where two pieces of tissue in the body, usually muscle or fascia, which is sort of connective tissue, align to one another. And those are those sort of things on ultrasound that doctors use to orient themselves while doing procedures, especially nerve blocks. A common nerve block with some big veins. That was a good target for me to sort of make a first model. What is the median nerve, which is just a nerve that runs down the center of your wrist here. So what I did is sketched up a rough median nerve model, just roughly speaking, using ultrasound to get accurate sort of dimensions. Did the exact same process, made it into a few different parts so that you could have fascial planes, printed it up on the good old pressa, made some bones that were also 3D printed that'll get stuck in there, poured it in ballistics gel, and before you know it, you have a sort of skin tissue model. An additional step here, because in addition to making the vessels, I was interested in making a nerve. I looked into different things that could be used to make nerves cheaply. Now, some of the common simulation model making companies will sell you fake nerves that you can put into your own models or into models that they sell. But those come at $50 a pop. And I'm not made of money. I don't have a $50 bill in my pocket. So I figured, what can we do to be cheaper? So I looked at a bunch of different materials, and yarn turned out to be a great option. Not by itself, because yarn has a lot of air in it, and air causes ultrasound to show shadows. But if you put it in ultrasound jelly or any sort of liquid, and then any sort of viscous liquid, and you pull out the bubbles via vacuum chamber, you end up with yarn without air in it, which is perfect, as you'll see in a little bit, for nerves. So at the bottom here, you can see how I take the pieces and I'm making the vessels themselves. So I seal one side of it by dipping it in hot ballistics gel. And then from the bottom, sort of using the capillary effect, allow sort of fill up the vessels to cause these little tiny, realistically shaped or realistically sized vessels. And then I just take a little hot ballistics gel and dab it over the top to close it off. And voila, you have vessels. Then we got to get a little messy. And this is sort of where I go into the whole making things in your garage, because while I am doing this in the simulation center, this is certainly not what I would call simulation center level cleanliness. And this is certainly not a highly robust and well thought out procedure. I'm just taking these pieces, getting my hands covered in ultrasound jelly, which is just there to cause lubrication, and sticking it all together, sealing the sides by dunking it back into the hot ballistics gel, and heat gunning it to melt everything together. Yeah. From there, I got one step further and realized that a really common procedure that is not well simulated, and even in highly expensive models that you can purchase, is superficial venous access. And the problem with this is vessels tend to roll. Anyone that's tried that will tell you, you try to get a needle into one of these little tiny veins and it just rolls right to the side. So once again, this invention and sort of innovation happened the day before Christmas break because I was really frustrated that a mold wasn't cooling quickly enough. So I just poured a bunch of ballistic gel over it to try to sort of smooth over the surface. Same thing happened. It didn't stick together all that well. But then when I peeled it off and put it back on after the Christmas break, I got a bit of a skin. And that skin, if you put a vessel under it, actually rolls and feels like skin. And so you can get a far more realistic feel for putting a needle into skin and having the skin move as you put in the needle, making it harder and more realistic. And of course, that makes it more fragile. But the wonderful thing here is if it breaks, which it will, you just toss it back in the oven and you have essentially zero waste. So let's have a picture and sort of prove to you that this ultrasound model I made actually looks realistic and actually looks like the model, looks like the anatomy. So on the right here, you see the rough area of the body that we're ultrasounding, and which is the median nerve sort of in the distal part of the wrist. And as you see, there are two bones, two clumps of vessels and nerves, and then one central vessel or nerve, which is the median nerve. So if we look here, you see one of the bones, the two vessels that are overlying on top of it. And as we go through the center to the other side, you see the two vessels and the bone. We go back through the center, you see that white thing, which is the nerve. You can look at it right here. And if I just go to the right spot in the image, there you can see. I'm not trying to mimic the body perfectly. One could. You could make this to have the exact right fascial planes you needed. They have them fit together and it'd be perfect. But you don't need to do that. All you need to do is have the right anatomical marker so that you can orient yourself and practice. And here's a picture that you can see of me injecting. Once again, not the best at it, but it is a pretty straightforward process to do. It's pretty usable, and it roughly works the same way as if you were buying one of these, $600, $1,000, maybe even more models from a company. So from there, once again, seeing, okay, this worked pretty well. The median nerve block worked pretty easily, and it was a pretty easy process to make it. And when I started making other models, and the process is the exact same. You work it up in CAD, you make silicone molds, you make the bones out of just 3D printed material, you make some ballistics gel pieces, you stick them together with ultrasound jelly, and voila. So here you have the ribs, you have the serratus anterior, and you have the latissimus dorsi, which are muscles sort of underneath the arm here for, once again, doing a different type of nerve block. You could use this same sort of model to practice more complicated things, or not more complicated, but more acute things, such as putting in a chest tube. Yeah. There's a variety of other different models that were made. In addition to those two nerve blocks, there are several other nerve blocks that are either in development or have been developed, but I'm not quite ready to show off yet. And on top of that, I figured, hey, why not innovate and add a variety of other things? So on the left here, you see a spine with 3D tracking bobbles on it because we're using motive cameras to connect this to a custom Python script that I've written to allow you to sort of track where needles are in real time relative to the models, allowing you to get useful metrics for how well a procedure is done. When I did that, I was like, hey, you know what medical students have a lot of trouble with? They have a lot of trouble with doing lumbar punctures on scoliotic spines. So I grabbed the CT image from online of a scoliotic spine, did a little Python magic, got the 3D file of it, and turned that into another spine. Another one is doing arterial lines. So all the vessels you saw so far were venous in that they're low pressure and aren't going to shoot back at you. But what if I want to have students be able to practice on an arterial line? So I just connected a tube with a syringe I can squeeze to the vessel. And voila, you have an arterial line. Kind of combining all the different things together here, we have something for a central line, which, as I think I showed you in previous slides, those sort of models will cost upwards of $6,000 to make something like this that doesn't even have movement tracking on it. And I can make this, and I did make this for under $100. And yet another one is here's a C-section belly that is used for our OB-GYN physicians to practice performing C-sections. But the problem is every time you cut it, you have a wasted piece of silicone there, which the company will kindly charge you $800 for. So you make it out of ballistic shell, and instead you spend, on average, $0 every time you do it because you can just melt it down and re-pour it. So yeah, that's what I did. The most expensive thing is obviously the Pressa printer, but that's just for the first model. And I can honestly say that even though the Simulation Center bought a Pressa printer, one of the nicer Mark IV ones for this, we've already made up the cost many times over in a single academic year. So yeah, that's that. That's my presentation. And this is really here to show you that with a little ingenuity and a lot of ballistics gel, you can save yourself a lot of money instead of having to purchase from companies these sort of models to practice procedures on. And hopefully that will allow you to more easily practice procedures and more easily be able to biohack your way towards interesting creative solutions, like subdermal insulin pumps, and the sky's the limit. Okay, thank you.